Okay, so we're very grateful today to be joined by Carlos Lange Bassani, and he's going to tell us about, well, I'll hand it over to you, Carlos.
Yeah, sure. Thanks, Adil. Let me share the screen here. Can you see the presentation correctly?
Yes.
Perfect. Yeah, so today I'm going to talk about kinetically trapped nanocrystals with symmetry preserving shapes. Main idea here is to talk about nanocrystal shapes. And whatever drives the interest of understanding nanocrystal shapes is plasmonic excitations, right? So whenever there is a metallic body with a metallic bond inside an electromagnetic wave on it, the electrons, they are mobile to follow the phase of the electromagnetic wave. And especially here, we're talking mostly about light. And if we do that with a nanocrystal, where the size and the shape, they are in a certain, they are compatible with the wavelength of this electromagnetic wave, then we have resonance. And this is what gives material function, right? If we look back in the classic materials in the past century, a lot had to do with phonons, with resonance in the crystal lattice. Now we're talking about resonance again to give material function in these nanomaterials, but it's a different type of resonances. It has to do with these plasmonic excitations, and the particle we are looking at are plasmons, right? There are many functions that people are studying. I think we are only scratching what this can bring us in the future. Applications that people talk about, for example, photocatalysis. So catalysis, the way we do it now is thermocatalysis. We need to take a noble metal, heat it up, spending a lot of energy as thermal energy, and then we increase a little bit the probability of some electrons jumping out of the noble metal and breaking bonds of this of chemicals, right? And catalyzing a chemical reaction. And with plasmonic excitation, what we can do is theoretically convert with a high efficiency photons into these plasmons, and then concentrating electrons and making them having a higher probability of jumping and breaking the bonds and catalyzing chemical reactions. So this is one of the big fields in literature. Other things that people can already do is using these plasmonic excitations for cancer treatment. So this has been done now in the past decade. Insert some nanocrystals, plasmonic nanocrystals, inject them in the cancer inside light, and this plasmonic excitation will locally heat the surface of the nanoparticles, killing whatever is around. So this locally heating is around 10 degrees, right? But it denaturates any protein around. And this is localized, so it will kill whatever is around. They even already had, I think the last number I heard, they tested in 200 human patients for prostate cancer. Numbers are really high, efficiency around 95% of cure. And they are now trying to regularize this in the United States. So most probably we are going to see many of these applications. Everything has to do with this resonance and has to do with the size of the nanocrystal shape. We can go even further. We can enhance this resonance whenever we think about a nanocrystal assembly. And this is what we call a superstructure, where it's a crystal where every part building the crystal is actually already a nanocrystal. So the nanocrystal will resonate with as a plasmonic excitation, and the superstructure resonate, the nanocrystals resonates between themselves, and then we can have enhanced function, right? And there is even this discussion in the literature of analogy of these nanocrystals assemblies with atoms, with the periodic table. So the nanocrystals, they are analogous to the atomic nucleus, and then we can functionalize these nanocrystal cores with ligands, which would be the analogous of electron shells. And then we promote interactions to lead to this superlattice. And people are even talking, we should do a periodic table of nanocrystals. Of course, this is an ideal situation. I think we are still far away from it. We have some recent review paper, collaborative with many authors in the literature, and we discussed this, what are the current advances, open problems. What I'm focusing my research in the past, I would say 3 years, is looking at shapes. So shapes here, they relate to these plasmonic excitations with the resonance with material function. And they also relate to anisotropy in interaction during these nanocrystal assemblies. And the length scale, the size of the shape will relate to the length scale of the superlattices. So yeah, I think even if we don't know exactly what to do with these nanoparticles yet, we know that shape is important. And well, in the past 2 decades, there was a tremendous advance into synthesizing these nanocrystal shapes with accuracy in shape, with monodispersity. And the field here is mostly composed of chemists and experimentalists. So they know how to, they have these recipes of how to cook these nanocrystals into different shapes. And well, they have from the simplest ones, those are the ones I'm going to be talking more today. They preserve symmetry of the crystal, and they can have either low index facets or high index facets. And then we have some more interesting shapes, 1 and 2D, they break symmetry from the crystal structure. We have multiple twins, forming, for example, decahedron and icosahedron, and even some more fancy, sophisticated features, branching and chiral features, right? I'm not even putting here the full citation. I'm just putting the head of the group, because every of these paper here would be like 5 to 8 authors working and trying to find the best conditions that maximize the accuracy, the monodispersity of one given shape. So that there's tons of work. But the main procedure here is we inserted a salt of a noble metal. So all these shapes are noble metals, gold, silver, platinum. Insert some ligands, some chemistry ligands and ions, control the pH, control the temperature, the cooling rate, and then optimize the formation of these shapes. And of course, here one of the technological barriers is we cannot use gold or silver or noble metals everywhere. So this would, I mean, noble metals, we know that they are scarce, they are expensive, there are several issues related to mineration and human rights problems. So of course, we would like for the society use, we would like to do plasmonic excitation with some cheaper and more sustainable materials. For example, people are studying manganese, they're studying copper, they're studying iron. But of course, controlling shape in an environment without being a noble metal is much harder. And then this comes to what I study. It's a theoretical framework to understand shapes, right? So, and I think this is something that is still missing, understanding why shapes form. And so we could then bring all this knowledge that we have from noble metal nanocrystal synthesis to any system. And the concept of why a shape form, it's an old concept already. It dates back from George Wolf, 120 years ago. He was a contemporanean of Einstein. And he is the responsible of this main idea that we think that shapes, they will form facets to trying to minimize surface energy. And this theory holds very well in the past century for mineralogy. But now if we look back here in the nano realm, in these nanocrystals, we see, well, all these shapes, the systems are very similar here. They are all face-centered cubic crystals. They are all noble metals that behave similarly. And the solution, the ions and the ligands are also, I mean, the equilibrium conditions are similar. Whatever changes here is the kinetics, and then it spans different shapes. So there is another more recent now theory of the kinetic wolf shapes. I mean, it's a basic assumption, facets with slower growth velocity prevail. And we have models, so we call those wolf-shaped constructions. We can now tell what is, by knowing the growth velocity, or not even the growth velocity ratio between different crystallographic directions, we can't find the shapes. Problem here is we cannot determine fundamentally what is the growth velocity. Whatever we have in fundamental science is the understanding of energy, right? So I'll ask in the community, what is the energy of gold? Some will say use a Lennard-Jones, and then some will say, no, you should use embedded atom model. This is better for metallic bonds. Some will say use density functional theory and a tabulated potential. I mean, we have the models, right? We are now choosing which model is best for energy, but how do we estimate growth velocity? Growth velocity depends on the environment. But we know from theory that for the shape, what matters are growth velocity ratios. So we don't need necessarily the absolute value. That already simplifies a lot the problem. The way I study that is with kinetic Monte Carlo. And I consider always in a simulation, the first atom, this is positioned in the middle of the simulation domain. And I allow these growth sites where new atoms can be grown to. Here they are 12, and they represent FCC structure, so a perfect crystal. And to each of these sites, I assign an energy, right? I calculate an energy and assign a growth rate based on the Boltzmann factor. And this positive and negative sign means that I can either grow or etch these atoms, right? The same way I grow a new atom, I can just take one out. And by doing that repeatedly, then the nanocrystal shape will emerge. Here is a video of the simulation. So we can see here the number of atoms being inserted. And this video is slightly zooming out and accelerating just to see how we can grow. And now we already see it's a cube is start forming. And one of the interesting features of this type of simulation, it scales very large, right? So I think here I will stop at 10 million. And 10 million atoms, they are around in the same length scale of these nanocrystals that I showed you from experiments. And this scales fast. So of course, there are many tricks here to do an efficient simulation. In my computer, whatever the system I'm showing to you today, it takes a few minutes to simulate a nanocrystal composed of 1 billion atoms. So then now usually what people do with these simulations now would define what is the system we want to study. So we want to study, I don't know, gold in an aqueous solution with a certain type of ligand, a certain type of ion, maybe test some different conditions and then find what are the shapes. And the proposal here is a bit different. We don't want to limit our analysis to any applied system. We want to understand what are the minimum requirements for different shapes to form. And then we came up with this hypothesis that, well, if it's the slower, if the facets with the slower growth velocity are the ones that form the shape, so whenever we relate that to energy, we need to look at the atoms that take the longer to be added to the crystal lattice. And those are the atoms with the lower energy, with the higher energy. So they have the smaller growth rate. So the hypothesis here is the hardest atom to grow in a surface is the first one whenever we have a smooth facet. It's the first atom that we call this an adatom. And in the primary facets, 1, 0, 0, 1, 1, 0, 1, 1, 1, they occur at, in FCC, they occur at determined coordination number. So what we propose here is we count what is the coordination number of the atoms, and whenever they are 3, 4, or 5, they represent, we say that, well, they represent these surface sites. Then we'll bias a little bit the energy to bias the growth rate. And from our hypothesis, this should be determinant to define any nanocrystal shape, at least the ones that preserve symmetry. And that's indeed what happens, right? So you have here all the simulations, they have slightly different energy levels of these low coordination numbers. And what we are finding here is any shape that is truncated by the primary facets, right? So we can have octahedrons, cubes, rhombic dodecahedron, and many of these shapes, they receive these funny names coming from geometry. Yeah, I mean, there's a reason for them to be. For example, dodecahedron means 12, dodeca, it's 12, and then it's rhombic because it's not a regular facet. This is a losangle, is not a square. And then here, if you look at tetra truncated, so every 4 facets, there is a truncation. So tetra is 4, and then every 4 facets, there is a truncation. So all of them have some funny names. And we can even have intermediary shapes between them. Yeah, I'll go back here in the video. So if you see here, it's saying grow. So I'm just growing atoms. And at some point, it will move to equilibrate. Whenever it's equilibrate, I'm allowing in the simulation until the same number of atoms is growing and being dissolved. So there is no net volume change of the nanocrystal. And this represents equilibration. But we see that even whenever there is equilibration, whatever happens, I'm going to put it again. Here, the cube, for example, whatever happens, the facets, they become smoother. The tips, the edges, they get truncated. So there is some energy relief. But the nanocrystal shape is overall preserved. So this means that these shapes, they are kinetically trapped in local minimum, right? And there's only a unique shape here, which is the octahedron with some small truncation in the tips. That's the minimum energy. And we can even just count here. I'm summing up the potential energy of every atom, and we see that some shapes have present a higher energy, but they are still the shapes, they are preserved because they are too large to transform into the minimum, right? So, and all these shapes, they preserve the symmetry of the FCC crystal. So that's what gives the name of the talk, which is kinetically trapped nanocrystals with symmetry preserving shapes. We can also, another important parameter here in this model is the bond energy, the ratio of bond energy to temperature, and it controls the roughening transition. So whenever bond energy is relatively large compared to temperature, the atoms in this simulation, they will try to find the best position to grow, and they will grow layer by layer and creating smooth facets. And that is the interest, right? We have interest in smooth facets, so those are the well-defined shapes. And then as we slightly decrease this bond energy ratio to temperature, we see roughening transition, rounding of tips and edges, isotropic growth into spheres. And there is even a limit to finding these pseudodendritic structures. And I call them pseudodendritic because they're not true dendrites. Dendrites, they form due to mass transfer limitation. And yeah, just a disclaimer here, this model doesn't consider any representation for the solution, so we cannot have true dendrites here. So what is the disclaimer here? We should never use this model in this limit of the pseudodendritic, and we should use another model, which is called diffusion limited aggregation. Okay, so we can do now that we have this tool scales efficiently. We have a hint. Adatoms are the ones, or the sites of importance to form shapes. We want to classify these shapes in, I call them shape diagrams. And well, what I do here, I'll simulate for varying levels of energy of atom nucleation. So every point here is a simulation. And I can then estimate what is the surface coverage of every type of facet. And when we see some some regions, they have some prevalent facets, and can use that information to build shape diagrams. So here is a shape diagram for irreversible growth. This means that I only grow in atoms. I never dissolve, I never etch any atom. And we can see here all the family of truncation between octahedra and cube. And whenever allowing etching of some of the atoms, so we're going to heal the surfaces, right? Of course, I'm growing more atoms than dissolving, so the nanocrystal grow, in average will grow, but there is still some relaxation of the surfaces. Then we see that this other region forming 110 facets, right? One thing here that often is the question in, there's always a common mistake. People call these a phase diagram. So this is not a phase diagram. This is a shape diagram. The phase is FCC. All these nanocrystals, they are FCC. The shape is different, right? But we can draw many similarities with phase diagrams. For example, in the Gibbs phase rule. Gibbs phase rule says that in a phase diagram, a single phase occupies a 2D region, and here in the shape diagram is a shape with a unique type of facet, right? But now, whenever we have a shape, for example, the cube octahedron has two types of facets, 100 and 111. And these facets, they also have a predetermined ratio of surface area. So they coexist in a line. And that is similar to solid liquid coexistence, there is a line. And now you can imagine already, whenever we are talking about three facets of a certain predetermined surface area ratio, for example, this is the truncated cube octahedron, it occurs in a single point. This is like the triple point, solid liquid vapor coexistence, right? So again, this is not a phase diagram, this is a shape diagram. But another similarity that we need to think, well, shape diagrams, they were important in classic materials because the phase diagrams were important in classic materials because they give the crystal structure, which relate to phonons, which relates to resonance and to material function. Now in the nanomaterials, whatever gives the resonance is the shape of the nanocrystals, right? And now we need to find shape diagrams. Well, how do we use these shape diagrams? I'm considering here the most simple model, right? Lennard-Jones in vacuum. That is the classic physical hypothesis. Let's consider the cow to be a sphere and floating in vacuum, right? So this is the simplest model possible, and why it's good because we can do it analytically. And I need a geometry. Geometry here for me, it's the FCC structure, and of course, this shape diagrams that I showed to you is only for FCC. And with geometry and the energy, now it's just some basic vectorial calculus. I can estimate the energy of adatom nucleation. Here I'm considering this Lennard-Jones for silver. And we input that in the shape diagram. It tells us it's an octahedron. So that is from the shape diagram. If I do the same, but I do the simulation, I also find an octahedron. And this octahedron has some truncated tips, 2.5%. This is in surface area. But just to disclaim here, this line here, this black line, whatever is below 5% of 100 truncation, I classified as an octahedron. So these truncated tips, they always exist to some extent. And well, this also agrees with everyone knows that the equilibrium shape of Lennard-Jones particles that form FCC in vacuum is an octahedron. So all the theory is somehow connected. And if we want to go to achieve these other regions of the shape diagram, we need to consider more things, right? So whatever I was considering there is this nanocrystal in vacuum. So there is only the solid pushing the atoms and holding them together. Whenever we insert these in a solution, for example, an aqueous solution, there are counter forces, and they are going to modulate the energy levels and the growth rate of some specific sites. And we know that now a few of the specific sites are very sensitive to the formation of shape. And if we want to even more explore more of these regions of the shape diagrams, then we need to insert ions. Ions, they go and they get stuck in some sites. So they have a strong bonding with some specific sites. And now these sites, we call them, they are kept. We cannot grow on top of these sites. Or even whenever we use ligands are these big hydrocarbon molecules. They absorb to the crystal surface. And now in order to grow an atom, we need to diffuse through the ligand layer, displace these ligands, and all of those effects, they modulate the kinetics, the growth rates. And theoretically, if we just do now a molecular dynamics, considering these effects, considering energetic models that we know from chemical physics, we should be able to find these energy levels, or even more, the growth rates of these specific sites, and then use the shape diagrams to have a first estimation of what is the shape of the nanocrystal. So that is one direction we are thinking now, performing this molecular dynamic simulation to go more and test this shape diagram theory. What I want to talk more today, it's on the transition of this shape diagram. And we have a first attempt of an analytic model. And the first step is to consider a geometric construction. So geometric construction of kinetic wolf shapes, this is the whatever dates back from 120 years ago. So from George Wolf. And what we need is a relationship between x. X is the distance of the facet with the crystallographic direction HKL to the center of the nanocrystal. And the kinetic wolf shape relationship, it says that, well, this facet will grow with corresponding to the growth velocity. And that actually, it's if we think about it, this makes sense, right? So the larger the growth velocity, the more distance this facet will be from the center. And if we do, for example, here's 1, 1, 1 is an octahedron, and a cube 1, 0, 0. And now we build the nanocrystal shape, just taking the facets that are the closer to the center. This relationship here, it's from the literature. You can find the name is Kristen Fichthorn. And the common kinetic wolf shape, instead of having velocity here, the one that dates back from 120 years ago, instead of having growth velocity, it has surface energy. So this we know how to do, and because this is a purely geometric problem, then we can find this analytic shape diagram. And this is the same as I showed you in the beginning of the talk. And it's just, I mean, it's a different representation. So the representation is ours, but there's no new science here. The problem here, right, as I mentioned, we are talking about growth velocity ratios, and we want energy. And so we need a relationship between energy and growth velocity ratios. And what I consider here is this growth velocity ratio is we have a certain number of islands, of growth islands growing concomitantly in each facet. And the number of islands relates to the time scale, to the time taken for adatom nucleation, which then relates to the energy level of these low coordination number sites, coordination numbers 3, 4, and 5. So this gives the proportion of how many growth islands are growing in each facet, and each of these growth islands take a certain time to grow. To help in the modeling, I'm using the simulations here. This is the same simulation, but it's just looking at the first layer of atoms. And there are a few things that we can observe. So first, the geometry of the islands in 100, they are kind of rectangular squares, and they follow the position of the atoms. All right, so the atoms, they are positioned as squares, and these growth islands, they are rectangular. In the 111, I'm going to come back here. They are hexagonal. But in the 110, they are lines. And if we look at the disposition of atoms in 110, they are also rectangle, but still these islands, they are only lines. And well, in the beginning, we thought it's just because of our simulation, we are considering only the first neighbor interaction. But if we go to farther neighbor interactions, this is Lennard-Jones, we still see these elongated islands in 110. And then we understood that that has to do with the disposition of atoms. They follow this zigzag pattern. So it's always easier to grow in the direction of these grooves than a parallel to them, right? It's easier to grow parallel than orthogonal to them. So this is the origin why they are elongated. And well, another thing that we can see here in the simulation, if we look at the growth time, they have this log linear scale plot. They have this asymptotic trend. And if we compute this growth time, we can find the growth velocity, and then we have the shape from the geometric construction. So to use this information in the model, well, we now say that the only thing that is affecting the growth rate, or the main thing affecting the growth rate, are the atoms, the growth sites surrounding the islands. We call those Lange atoms. And I consider that I'll consider a continuous model, even if atoms are discrete, but whenever we upscale, we're going to consider continuous mathematics. So whatever I need is the perimeter of these growth islands, and I assume these growth islands to have a very simple geometry, right? As squares in 100, hexagons in 111, and just simple lines in 110. And then we can compute the time an island takes to grow, n atoms. So here we can see this is the Boltzmann factor, and this energy, the coordination number 5, these atoms surrounding these islands, they have coordination number 5. This is for 100 and 111. And this phi here, this is a parameter that relates to the geometry. So phi in the 100, so this relates to the perimeter, is 4, because a square has 4 sides. And then square root of n, this n relates to the surface area of is the number of atoms in the growth island, so that relates to the surface area. So everything is very simple here. And this model is able to capture all these growth velocity trends compared to simulation. It captures the trends. It does not capture the absolute values, though. And I do not expect this model to capture absolute values, because to capture absolute values, we need to tell what is the size of the facet. And this model doesn't require any size of the facet. So this is a con of this type of modeling. But it can capture the growth velocity ratios, not perfectly, but it can capture. And that is what we need for shapes. So we have now, this is the analytic model that I'm talking here, that we can transform velocity, energy to velocity, right? There's some coefficients here, and the coefficients are a little bit ugly. But again, bear with me, it's just always talking about some Boltzmann factors, and some here, this 4 is because it's a square. 3.72, I can see this is an hexagon. It's not so easy to see, but this is an analytic value for an hexagon. And if we use this analytic model, we can now transform that shape diagram that was based on growth velocity, that is in the literature for 120 years already, into energy. And that would be the link between energy, growth velocity, and shape, right? So here are the two shape diagrams that I'm talking to you. So one is the simulated, the other one is the analytic. And of course, there is no perfect match. We don't expect any perfect match, but we can see some features, right? This analytic model captures, well, there are three main regions. There is a larger transition region between truncations of octahedrons and cubes. And overall, it even determines here these transitions. For example, this one is at 45. And we can see that in the model. This 45 line happens whenever B is close to unity, right? So the tangent of 45 is 1. And that actually, this is close to unity, 0.93. This is the ratio of the perimeter of a square and an hexagon. So this is coming from the geometry of the Grove Islands. Right, so this model is not perfect, but we need to understand here that there's a fair large degree of simplification. We are talking about steady state growth. We have all the simplifications of geometric constructions. We have this simplification of perfect islands. There are squares and hexagons, and we have a continuous model, but it still captures many features. And this drives us to the conclusion that only the growth rate of some specific surface sites that drive the formation of these shapes, right? What are these surface sites? Primarily adatoms and secondarily the large atoms around the growth islands. And the geometry of the growth islands is also important, right? And if this would not be correct, this model would be completely out, right? So we are capturing the main features. So this means most probably we are capturing, at least this model is reproducing the simulations. The simulations for us are the computer experiments, right? What this means practically means that whenever we think about nanocrystal synthesis, now we want to go back to reality, synthesize a nanocrystal that I want to have the best rhombic dodecahedron. So I need to select the solution chemistry that act on those sites and not anything else, right? So that is what the theory is telling us. Yeah, more here you can find, and we have a preprint now in arXiv. Name of the paper goes by the same name of the talk. And I would like also to thank the people involved. Here, the main person involved here is Michael Engel. Michael Engel is the PI of the group here. I'm working in Germany. He is the responsible of having all these nice ideas to have upscalable and efficient simulations. He also, I mean, maybe 2 years ago, he came with this idea, Carlos, I don't know, but it has to do with coordination number. We need to look at coordination number. And it took a lot of time to understand that is about adatoms, is about large atoms. But Michael already had this feeling that it had to do with that. So that was a really good lead. And then also some students, they're now pushing forward this work. Kamila Zaripova, she finished the master thesis and she was testing allowing stacking folds forming during growth. And then she found already some symmetry broken shapes, tetrahedrons, nanorods, nanoplates. Then Jarui is finishing his master thesis. He's studying the formation of high Miller index facets. And Giotti, she started a PhD this year, and she's now looking at twins and geometrical frustration, and she already could find the first decahedron, which is a multiplied twinned nanoparticle. And hopefully in the future, we are going to see some more shape diagrams here. Thank you very much.
Thank you, Carlos. That was fantastic. Allow me to thank you on behalf of all our participants today. I'm going to stop the recording now and then we'll hand over for questions. So I've stopped the recording.